Okay, let's get back to the class. I really wanted to quickly just reflect on the midterm first. So we graded it. I think yesterday we released the grades. Overall, I think the result is positive. I mean, that's what I expected. So out of max 78 points, someone achieved 77, which is great. I mean, as I said, we are not super strict, but we are reasonably strict graders. So it's kind of totally reasonable that we have a bunch of people over here, and our mean is 51, which is somewhere around here, right? So overall, like people are above the mean, which is which is great, obviously, right? What am I saying above the mean? It's probably you cannot mean is exactly in the middle, right? But I mean, I'm not surprised. So that's a decent result, or even good one, I guess. Any questions? And I mean, we set, I think we set 77 as a max possible grade, kind of curving a little, but it doesn't really probably affect that much. Any questions about this? All good? Yeah, it's open for regrade, so feel free to submit a regrade request. Feel free to ask us questions if something is unclear, but let's keep going then. So our goal for today is quickly to finish system calls, right? And exactly what we were doing last time, we were looking at those functions which check the system call arguments, right? Because the kernel itself, so something when you invoke a system call and pass multiple arguments, so let me show you where, for example, somewhere over here, for example, it's a syswrite, which we were looking at. So here syswrite takes 3 arguments. So this is a file descriptor, this is a pointer to a buffer in user memory, and this is the size of this buffer, right? And so obviously, if the kernel just blindly takes those arguments at a face value, it opens an opportunity for an attack. So this buffer pointer can point anywhere, and specifically, like probably a read system call would be a better. But even like a read system call would be a better candidate, because read can specifically take data from disk and read the data into this buffer, right? And if this buffer happens to be a page table, then user can control what gets written to this page table, right? That makes sense. And of course, it's a very kind of like rogue way to abuse the kernel, but like multiple nuanced ways exist, right? And so essentially what the kernel is doing, the kernel will always carefully check for the sanity of those arguments. So, right, and x86 provides a collection of those functions which specifically say, okay, hold on, for each different type, I will be carefully checking what's going on. And here specifically, they use a function which fetches a file descriptor, fetches an integer, this is just the n itself, and fetches a pointer into a buffer. And a pointer into a buffer has to take 2 arguments, the pointer into a buffer itself, but also like, it's not like that. So the pointer will be, it says, okay, fetch the argument number 1, but we also make sure that, and it will be a pointer, and we expect to fetch a pointer of size n. And we already previously checked the size n here, because in C, if you remember correctly, those guys are executed in this order. So first you do argfd, then argint, and then argptr, right? So that's not a coincidence. So, I mean, maybe it's not the best way to write it, because like, unless you really know that it's executed in this order, you might get confused, right? So it would be cleaner to write it as a regular, like line by line code, 3 checks, saying, okay, we first check the size, then we check the pointer. But you got the point, right? We understand this? Do we remember how those functions work? How you fetch an argument from the user call? Remember, there was additional interesting detail here. The syswrite, it's a void function, so it doesn't take those arguments. How do we pass the arguments to the system calls? Anyone remembers? Correct. So we pass system call arguments on the user stack. So what specifically happens is that when the user invokes a syscall, remember there are two stacks. One is currently pointed by the ESP register, and the one which sits in a kernel, which is pointed by the TSS, whatever, ESP0 or whatever the pointer is. And this is the kernel stack of the program, and this is a user stack. And when the user is about to invoke int x40 instruction, which will provide the user with the option to transition from privilege level 3 into privilege level 0, where the kernel is running, right? Before doing that, the user just, the compiler for this function just generates a general call site, which says, okay, I will push those arguments on the stack. So at the very top, there will be, at the very bottom, top of the stack, will be 1, the file descriptor pointer. Then above that, there will be a buffer. And above that, there will be n, right? And after that, since the way we did the plumbing, there will be also a return address here on the stack, right? So ESP will actually be pointing for the return address. But after that, the user code executes the interrupt, and everything switches to this kernel stack. Remember, we looked at those functions, vector 64, all traps. From all traps, we go into the trap. And while being in this assembly code, we carefully save all the registers on this kernel stack. And specifically, one of the fields there will be an ESP value. It's actually saved by the hardware, right? So ESP value will be pointing back to this user stack, right? And so that's why, although we switched the stack, the hardware did the switch for us while executing an int instruction, we still have access to the user stack because we have the pointer to the user stack, because this value of ESP, which was inside the hardware register, got saved here on the kernel stack, right? And so cool. So after that, we know that, sure, user passed the arguments on the user stack, plus we have one additional value here, 4 bytes of return value. And so if we want to access argument number 0, for example, we're shooting for this line in memory, right? So which we'll get as ESP plus 4, right? Because ESP, user ESP, which points exactly at the return values plus 4 points to 1, right? And this is exactly what these functions are doing. So let's go over again. So real quick here. So this essentially a function which fetches an integer, which is, in our case, it's argument number 3, which is n, right? So, oh, sorry, we're counting from 0, so it's argument number 2, argint. So, and what we do here, we say, look, please fetch this value from user memory as an integer. Since we have access to the user value of the stack pointer, the trap frame data structure, which is currently linked from the current process, because we saved it there while entering the kernel in the all traps and then in a trap function. Plus 4, this is the return address, and then 4 multiplied by n. In our case, n will be number 2, so it will be 8 here, and we're saving it into this location in memory pointed by this instruction pointer, by this integer pointer, sorry, right? And of course, this fetch in function, which I was explaining last time, it does a couple of checks, and this is where specifically we stopped last time. I mean, I briefly explained it, and we were discussing this question of what happens. Sorry, let me scroll real quick. Sorry. Where's my pen? So those checks are like this. We say, look, this address which we're passing here, so specifically this address which is computed here, and we pass it as an argument in address, has to be within the address space of the process. And moreover, not just the address itself, but the address plus the size, which is 4 bytes, right? Otherwise, there is a chance that we're going to overflow, right? And so if process address space looks like this. And today our second part of this lecture is constructing a new process with the exact system call. We'll see that the size of the user address space is tracked with this variable, which is part of the process data structure. It's called a size, SZ, and it points here. So we have to make sure that all 4 bytes are contained within the user address space. Moreover, not just lower than 2 gigabytes, but really it cannot be here because this memory is not allocated, and x86 actually doesn't handle page faults. So essentially, if the user passes a pointer to an unallocated page, it's a page fault, and x86 doesn't really know what to do at this point. It will just halt itself. But this +4 trick is that you need to make sure that the user cannot pass something what ends at the edge of the address space, and the last 3 bytes overflow, meaning that they will be somewhere over here, right? Make sense? And so we were talking about it. And we looked at the integer value, which we just discussed. So this one, and then to fetch a pointer to a buffer, an additional check is that, like, the buffer itself, so the pointer itself, P, and the entire buffer, N, has to be within the address space. So for example, x86 does it this way. So it says, okay, we first fetch the pointer itself, right? Because the pointer, the way we pass a pointer, it's kind of roughly similar to how we pass an integer, right? So it's just on a user stack, right? And so we have first read those 4 bytes from the user stack. So we're carefully reading them because otherwise user can attack us by passing a pointer itself. And then when we got the pointer into this I variable here, we do this check that we're saying, okay, hold on. We are trying to validate that the entire buffer, so entire size, is within the user address space. So now instead of just blindly doing this +4, we check for the pointer itself and a pointer plus its own size. And after that, we say, okay, at this point, we know that the pointer is contained within the user address space. So it's okay, and we will pass it back to the user, pass it back to the calling function saying that we validated it. Make sense? So in practice, like each system call has to make sure that there is some kind of validation of the arguments, right? Otherwise, you're opening an attack, an opportunity for an attack, and specifically, like. What I wanted to say that like it gets pretty hard because semantics of these arguments in real kernels. I mean, and x86 is not that far from being fully featured or close to illustrating the point of a fully featured kernel. But those checks, like you can imagine, can get quite involved. So I think this is what I wanted to explain about the system calls. So any questions about? Like for the last 3 lectures, at least, we were talking about interrupts and then system calls. Like we talked about how the hardware implements it, or what interface the hardware provides, essentially all this interrupt descriptor table, global descriptor table, TSS, kernel stack, how we enter the kernel, how we switch between privilege levels. Then we looked at the implementation of system calls within the x86 kernel itself. And now we're kind of done. So like at this point, we know how, if we were to build user processes, we know how to build an interface in such a manner that they can invoke the kernel carefully and securely. Any questions about it? We're good? Okay, so if we understand the system calls, so that's, we are well positioned at this point to essentially move on and talk about what does it really mean to create a process. So again, just kind of recap of what we learned from the beginning, right? So what we were doing is the following. So we said, okay, look, we start on a bare CPU, right? So we like even the state of the CPU in some it's some weird, we don't really know what's going on. So like there's a lot going on before BIOS kicks in, all this system management mode, Intel management engine, stuff like that. After BIOS executes, it essentially passes control to the bootloader. And this is the first thing which we control, right? In many cases, like in your homework, for example, when you were booting in Hello World, instead of this bootloader, we said, okay, you can feel free to use a grub. It's just easier. And grub was this bootloader for you in that homework. At some point, we implemented we implemented like a specific protocol which grub understands, and the name of this protocol was multi-boot. But okay, we put it in a bootloader. Bootloader took the kernel binary, kernel from disk, loaded it in memory, and jumped to the entry point. The kernel itself just did a little bit of magic. It set up global descriptor table, entry, page directory. But essentially, our goal was we got to the main function, right? We set up the stack, obviously here, stack. Kind of very similar to what we'd done in a homework, right? Remember, it's just one fetch, execute, decode, fetch, decode, execute loop on the CPU. So the CPU started from power on, despite the fact that there was like some magic was happening from Intel. Conceptually, it's just one thread of execution. So really, it's just one thread. We didn't do anything. We disabled the interrupt in context switch. Despite the fact that like x86 wakes up other CPUs, we're going to talk about it later. So let's just imagine we have CPU 0 for now. And we reached main, right? And inside this main, what we talked about, that we set up the memory allocator. So it's a linked list of pages available to us. So which we can allocate with malloc and free functions. And we also set up interrupt descriptor table, so meaning that we can actually process interrupts and process system calls, stuff like that, right? And like x86 will do a little bit of additional initialization. We will cover it later. But at this point, we kind of understand that, okay, we know how to construct a new page table, because we switched from the entry page table directory to something what we call the K page dir. So it's a kernel page table, which is fine grained 4 kilobyte pages page table. And at this point, we can do whatever we want, right? And what makes sense to do at this point is to learn how to construct a new process. So essentially, we know that main will continue running in privilege level 0. And but the whole point of the operating system is to make sure that we can allow users to write their own main functions. And essentially, every time we want to execute a process, we create this new address space with privilege level 3 and pass control to the main function of the user, right? And after that, the user runs, does whatever they want. And if they want to enter the kernel, we have a system call, right? And system call like a read or write. We will build a file system a little bit later. But essentially, we're kind of close to completing this idea that we can figure out how to run user processes or user applications in a secure manner in such a way that each process is isolated from each other and the kernel is protected from the entire user land. Make sense? Do we understand where we are? So today we kind of skipping a couple of steps here, like final initialization. We'll come back to it. But we're going to discuss the exec system call. Do we remember what exec is doing? Anyone? Exec replaces a new process with a new executable. So exactly. And at a high level, if I ask you, how can we do it? If I assign it as a homework, what will be inside? We already know how to enter the kernel. We already know how to get to the entry point of the exec system call, which we will call a sys_exec. But what will be the logic of the system call? What do we need to do inside? So you're saying load the, like, okay, so the process itself, let's, for the sake of example, say something like bin/cat, sits as a file on disk, right? So it's an L file, right? It's in a file system. We don't know yet, we don't know how the file systems work, but we know that we can probably read something from a file. You're saying we're gonna load it in the address space, which means that we kind of have to create this address space, right? Agree? A new one. So first of all, let me just make sure that, like, if there is a process which is already running, I don't know, maybe it's a shell, for example, and it has an address space already, so it has its own text and data section, has its own like stack here. And at some point it like calls into the kernel saying, okay, please exec, right? In practice, you say, look, we can, you say, we're going to replace the entire, what you said is what we're going to replace this, the address space of the currently running process, right? There is a little bit of a problem here. So who can point me out what can go wrong if we just blindly start replacing? Anyone? But this is what you were suggesting, if I understand it correctly. You said replace the address space of a process. I'm saying it's not trivial. You cannot just simply replace, because there is like a weird implementation detail here, which is kind of, the moment you start coding, you immediately realize, okay, hold on, it doesn't work this way. So what can go wrong? Do we see an issue here? Well, imagine exec can fail, right? So maybe you ran out of memory. Maybe the user is a bad guy, and they like said, okay, like this is a giant file, and maybe halfway through loading it and replacing the address space, you ran out of pages on a memory allocator, or maybe some of the arguments, maybe this file doesn't exist or something like that. If you start replacing this address space page by page, saying, okay, look, it's a new address space, and I will just be throwing away the old one, it's kind of problematic, because if exec fails, ideally you should go back to the shell and get an error saying, okay, well, exec failed, but there is no shell anymore because we started replacing it, right? An obvious solution here is that, okay, sure, instead of replacing the new address space, the old address space, we'll create a new address space, like a fresh one. And if we're lucky and this guy will go and everything is successful here, all the pages are allocated, we'll get a new process. And we will maybe destroy the old one at this point. Because at some point you say, okay, we committed that everything went smoothly, and we can say that the old one is thrown away, right? So that's how we're going to do it. So we say, look, we will start building a new address space, a new process effectively. And we'll, as you say, it makes sense. So we're going to load this file from disk, essentially in the address space, very similar to how we did ELF load in this toyish ELF exercise homework, right? So it's kind of the same thing. And it's at a high level, it's not super duper hard, right? There is, however, a couple of interesting details. Let's just talk about them. First of all, right now, or when we boot it, right, like in this main function, remember that in this main thread of execution, when we started from BIOS, essentially, our kernel page table represents this address space. It doesn't have anything in the lower part. It's just empty. And the kernel itself is allocated at this kernel base plus 1 megabyte, which is like 2 gigabytes plus 1 megabyte. And we have the like a little bit of a gap below for the BIOS, where we can write something and print hello world on the screen. And then we have a kernel text, kernel writable data, and some free memory. And we, up until now, we talked that we allocated memory up until n, but later on, x86 actually like grabs all the memory up until fizstop, which is 234 megabytes, right? And sits there. And like it doesn't do anything here. So this is unmapped. And the tiny BIOS region is mapped at the very top of the address space. So on purpose, we left this part of the address space unallocated. So this is where the user process, user main will go, right? And that's okay. So right now, this kernel part is allocated. We use it in this kernel page directory. And our goal today essentially is to learn how to manage this lower part of the address space, right? So essentially, more specifically, the way we'll be building this process is that we will say, look, this is exactly the layout of the address space which x86 implements. They assume that the kernel text section is compiled and linked to run at address 0, right? So main doesn't have to be at 0 address because the compiler can put main further in the text section, but roughly speaking, main is here. So the process text section starts at 0. Process data section is above it. Above this, we will have a tiny guard page to protect the stack from overflowing, and the stack user stack will be sitting right on top of it. This guard page is exactly 1 page, so it's 4 kilobytes, and the stack is exactly 1 page as well. It's 4 kilobytes. And this other part of the address space will be used by user malloc. So it's your heap, right? So the heap will be growing towards the top of the address space, and that's fine. You have as much as up to 2 gigabytes of memory for a user process in x86, right? So this is exactly how we want everything to run, right? So it's a design choice. You can make different design choices, but this one is reasonably good one, right? However, just to make sure that we all understand, since we already talked about syscalls, the address space of every process, right, will have these 2 parts, because when you even create a new process data structure, and inside there will be some kind of a page directory pointer, which points to the page table of this process, right? And each process will have its own page table. We understand it, right? The complete address space of the process will contain both kernel memory, so it will contain both this yellow part, and of course it will be from disk. When we will be initializing the process, we will load this process stacks and data, set up the stack, so it will have this green part as well. Again, it's not really strictly required to make sure, specifically ensure that this yellow part is mapped. But if we recall, now we understand enough about the interrupts. The way the interrupt mechanism works, so for example, either user invokes an int as a synchronous thing, x40, or a timer interrupt arrives. Remember, the hardware itself says, okay, I have an interrupt descriptor table, and it kind of immediately will jump to the interrupt handler. So if you don't have this yellow part, then you don't have the interrupt handler mapped, right? And then, then what you're gonna do? You have to, modern operating systems don't always do this mapping, so they can map just a tiny trampoline code which switches to a different page table in which the interrupt handler is mapped. That's okay. It's called in light of these meltdown and Spectre attacks. So essentially, the defense which was introduced was kernel page table isolation, so KPTI. So this KPTI is the idea is that the kernel memory is not on a page table, because if you understand meltdown, then meltdown allows the user process to read the kernel memory through some speculative execution mechanisms in the CPU. But that requires this yellow part to be mapped by the page table. If you say, look, it's not mapped, then meltdown doesn't work. But it makes everything slower, because on each system call, you have to switch a page table, because the user, the program, the processes, the page table of a process doesn't contain this yellow part, just to protect it. But switching a page table is a rough business. So it's roughly if you switch here and there, it's roughly 800 cycles. And if you just which means that you lose 800 cycles on each interrupt or on each system call. So KPTI is okay, but it's not ideal. I don't know, that's why for simplicity of the argument, we say, look, each process will have the kernel part of the address space is mapped in the address space of each process, which allows us to implement system calls and interrupts in a simple manner. We don't really have to switch the page table. We can use just the same page table. We just switch the privilege level from 3 to 0, and suddenly the yellow part becomes accessible, right? Make sense? Anyone heard of KPTI before? Come on, KPTI is a big deal. I'm pretty sure that you've heard of it on a variety of websites dedicated to security, and I don't really have time to really go into the details of this idea, but the idea is to block meltdown. Okay, if I ask differently, how many people understand how meltdown works to begin with? Okay, yeah, okay, so we might have to come back to meltdown at some point. But okay, the point which I was trying to make is that the address space of each process will have two parts, user part and kernel part, and the kernel part will be the same for each process in a system, right? Okay, so now if we're back to thinking, okay, like we have to build this exact system call, right? Sure, that doesn't seem too hard. So it just takes a couple of things like the file path to the process we want to run or want to exec into, and arguments which are represented in some funky manner. We'll come back to it later, but it doesn't matter for now. Sure. So at a high level, everything is as you were discussing. So you said, okay, sure, our goal is to construct the new address space, and more specifically, this contains of two parts, right? So the kernel part, sure, we already know how to build the kernel part because we did it when we were building the first kernel page table, the first real page table for the kernel. And the user part will be building as we were going through a file on disk, we will be just allocating pages, putting them here, and loading them immediately from disk into the user part of the address space, right? Make sense? So that doesn't seem too hard. So essentially just roughly speaking can be summarized in this like three bullet points. So load the program, create the address space, load the program from disk, allocate the user stack, just because like the execution runtime of a like simple C program is just a stack, and then we can run. So essentially just say your instruction pointer will be pointed here. And if I ask you a question, how do we start running the user process? How do we load this instruction pointer in the CPU register? Do we remember how to do this? In fact, remember we creating the process inside the kernel. We're running with current privilege level of 0. And we kind of want to switch to privilege level 3, right? In user land. This is where our instruction pointer should be pointing to the user main function, right? So how do we initialize? And this has to be the value on the CPU. So how do we load the instruction pointer into the CPU? We talked about it briefly. Jump with a CS of a user. That's a possible way, I would assume. It's not how it's done, but that probably can be done this way. For simplicity, we use IRAT, because IRAT immediately loads both the kernel, the instruction pointer and the stack pointer, and switches both the stack segment and the code segment. However, it's a great exercise, and actually, I mean, why not? I'm like, let's do it. Let's do it as an extra credit, some kind of a number of, I don't know, like, let's say, what is it like? What is it worth, do you think? 2% of your class? Great. I mean, maybe 3. Replace, and I mean, towards the end of the class, it makes sense to start opening up this as extra credit assignment. So like replace IRAT with a jump and see if it works. And it should work, but let's do it. Like, I don't know, never done it myself, but most likely will work. And it's a nice kind of exercise. Okay, so yes, we're going to be using x86 uses our read instruction to load this user instruction pointer. Okay, just again, back to high-level overview for a second. At a high level, what we need to do is to say, look, inside the exact system call, we will read the process binary from disk. It's an ELF file. To read the ELF file, we didn't talk about it, but the file system will provide us with a function which is called namei. Namei converts the human readable name like this, /bin/ls, into a pointer to an inode, because the file system internally represents files as inodes. Don't worry about what it means right now. It's just like really just a file without a human name, because a single inode can have multiple human readable names in multiple places in a file system. Then we're going to read this file block by block, and the file system will provide us a function which is called readi, stands for read in inode, right? Fine. So, and it reads into memory, right? However, in order to read this file into memory, obviously we say, look, instead of like reading in a temporary buffer, then copying somewhere, we will simplify a little bit. And what we will be doing is that we will already construct an address space of a process. So meaning that we construct a page table, and we will be allocating pages in this green part of the address space, right? So specifically, we will be saying, okay, every time we want to read something from disk, which is like a file, which we say is represented as an inode, every time we want to read something, we will allocate memory here. Like if we want to read a process text action, we will allocate this several pages and just directly read this ELF file into this memory, right? And if we're careful with this, like we compile the files that everything is linked statically to run it at res0, we don't have to relocate anything. We don't have to do any linking, any position independent code. Everything is simplified in x86, right? But sure, why not? We're just gonna do it. And after that, you're ready to, like, you have an entry point, which is typically main. On x86, it's always main. We just then say, okay, user instruction pointer will be equal to the entry point of this ELF file. We'll set up a stack and we're ready to go, right? Make sense? Again, conceptually, if you already did the homework number 2 ELF and you did, like, you carefully followed the lecture, it doesn't seem very, very hard. Like, creating a process seems like a reasonable adventure, which can be done as a homework. Okay, now we got the high-level picture. Everyone, any questions about it? We're gonna dive into x86 source code from now on. We have a high-level overview, understanding how it works already, right? Not hard. Okay, exactly. So it's a source code of the exact system call, takes 2 arguments, the pass to the file, and a pointer to a pointer argument array. We cover it later. But essentially what x86 is doing, sure, it says, okay, I will take this pass and I will use this namei function of the file system, which converts it into an inode. If it exists. If it doesn't exist, it just says, okay, error, we're gonna exit. Sure. After that, we say, look, we assume that we're gonna read an ELF file. So similar to how you were loading the ELF file in a homework, you say, let's read the ELF header first, right? So you say, look, I will be using readi, reads an inode. And inode at a high level is just to think of it as a translation data structure, essentially kind of like a page table. It takes the address in the file and it has kind of like a tree which points to different locations on disk, because the logical block, like the logical address 0 of a file can be in a physical disk block, I don't know, 55, right? Or something like that, because files are all over the place, allocated out of order, but it's kind of like a page table, but converts from logical file addresses into physical space on disk, right? And it says, okay, look, sure, let's read the ELF header, size of ELF header, not super hard, and check if the ELF magic is like matches, then most likely it's an ELF file. We can move on. We're trying to load it in memory. But of course, like, remember, like, it can go bad, right? And you have to be careful. Next thing, okay, we checked it's an ELF file. Our goal is to create an address space, right? So we say, look, sure, we're gonna construct a new address space. And as I was saying, the address space of every process in x86 and in any typical operating system consists of two parts, the kernel part of the address space and the user part. Well, let's first construct the kernel part, this yellow part, right? And we already know how to do it because we did it once. And I was kind of hinting that we're going to reuse this function multiple times. So remember what we just entered the main function. We already seen this function before, set up kernel virtual memory. So it's essentially, this is how we constructed the first real page table in x86, right? And more specifically, I will just remind you how it worked. What it does, it says, okay, well, I will allocate a new page for the page table directory for the root of the page table. We've already seen it here. Remember, it's when we called it from main and we like allocated, like we called kv malloc function, and then this setup kvm was called from there. Okay, so we allocated a root of the page table. We zero it out, saying that, okay, it has to be clean. And then we did this loop. Remember, we used this data structure called map. It's called the kernel map, and it contained 4 elements. And essentially, we said, okay, we're going to invoke this map pages function, and map pages will take the region from a kernel map. So it will start at a specific virtual address, will have a specific size, and we're gonna like map this specific physical memory into this virtual address with specific permissions, right? We've seen it. That's how we did it last time. And internally, everything was working like this. So you loop through this kernel map. Kernel map has 4 regions. The BIOS region, which is read-write here, the kernel read-only region, the kernel read-write region plus up until the fist top. And finally, the 4th region was this BIOS region at the very top of the address space, right? So not a surprise. So we're just simply reusing the same function. So every time we want to construct a new process in x86, we say, look, reuse this function, construct us a new page table, which has the kernel address space mapped. And just to be specific, that was the kernel map, array of 4 elements. Remember, we talked about it a lot. And just for each map pages, for each element, we invoke the map pages function, and everything runs smoothly, right? Any questions about the kernel part of the address space? Okay, sure, we got it. So now for the user part of the address space. So essentially, specifically this green part, which we were discussing. So right now, like when we finished with this setup KVM, we just got the yellow part. The green part is completely empty. So our outline will work something like this. At a high level, for each page of the user part of the address space, we want to allocate the pages, meaning making sure that we got them from the memory allocator and map them in a page table. And then we're going to read data from the inode, like specifically kernel text, data section, stuff like that, into those pages, right? Again, it kind of sounds like, sure, like not super hard. You already had this yellow part. We have a page table which maps everything, right? So that's what we got out of this setup KVM function. And now we will be just allocating those pages one by one and reading from the inode the L file into those pages. Make sense? Not super hard. Okay, so sure, like let's take a look at this loop. So not surprisingly, it's very similar to your homework number 2. So you have an L file. L file has what? What do we read from the L file? Does anyone remember at this point? We're going to be reading program headers because section headers are for the linker, right? So we're not going to relink anything. We already believe that everything is linked correctly. So we first read the program header table, and then for which is an array of program headers, program sections, right? And then we're going to be reading them one by one. So what we're doing here is that the L file has, okay, just a reminder, program header, we had the magic here, we did it. The program L header has a pointer to the program header table. This is just an array of entries, and those entries point to everything what needs to be loaded in memory. And section header table, we don't care about it because we're not going to link anything, right? But essentially, we're going to build the loop, and this loop just goes one by one, right? So it's, again, not super surprising. So we say, look, starting with the offset, like remember the elf header has this field, ph offset. It's a pointer, just to make sure, this is the pointer to this program header table in a file. Starting from this address, we're going to be, elf also has the number of elements in this table, right, in this array. So we're going to be looping for this number of elements. And we're going to be incrementing this offset by the size of entry in this array. So essentially, if we have an array here, we know the number of elements, we know the beginning of the array, number of elements, and we know the size, and we're just looping through them. Very similar to homework 2. So we say, look, like, sure, we're gonna use this read inode function to read one element of this array into this ph program header variable, like at the address offset from a file and the size of a program header, right? And if the read fails, sure, we again go to bed. And at this point, this is useful that we allocated a new page table, because we didn't overwrite anything, but at least, you know, we can fail. And since we're in a loop, we start reading, we at some point, we start overwriting the address space, right? Okay, so we got it. So we go and read one by one. The question is like, okay, we originally, at the beginning of the loop, we just read the entry from this, but this entry will point to part of the elf, which we really have to load in memory. So this goes into the user address space, right? Of course, we still don't have memory in the user part of the address space. So that's what we're going to do next. We say, look, at this point, it makes sense to allocate this memory. And we use this function, which is called allocuvm function, which takes a page table as an argument. The other arguments is the current size of the address space. It starts from 0. Remember, I said that there will be a variable which will be tracking how much memory we allocated. And essentially what we do next is that we say, look, and like after allocation is done, we'll get a new size. But the idea is that if we said we allocate like enough space to load this specific section from disk, from elf file into memory, then we like this simply allocates memory. The second function loads it from disk. And what it says here, okay, sure, just within the file, this is the offset within the file and the size of this section. Use this inode and please load it at this virtual address. And please use the page table as an argument, right? So what happens specifically is that allocates these pages in user address space, load UVM, loads them from disk. Again, not super hard, but interesting. So let's quickly take a look at what allocate does internally. If I ask you a question, again, what's the internals of the allocate function? And just, it's kind of a recap of what we talked about maybe like roughly 3 to 4 weeks ago. What's inside this allocate UVM? How do we allocate pages and how do we add them to the address space? Correct. We're gonna allocate them. So we have a free list of pages. So we first allocate maybe page by page, right? And then we essentially say, look, we have a page table and we can just essentially say, we have to update the entry in this page table. Like if we got this page from the linked list, we have to make sure that this entry in a page table points to this specific physical page, right? Makes sense? However, there is a little bit of magic. First of all, we need to account for the virtual address at which we're mapping this page, and like to make sure that we're correctly allocating everything in the page table, correctly updating, maybe potentially allocating inner parts of the page table. And finally, even if we got the virtual address, we need to switch to the physical address and essentially assign it here with some kind of permissions. And this kind of relates to what you just did in your homework number 3, because you said, okay, you put it into main and you created a simple page table. You ran in a loop mapping the first 8 megabytes, right? But it's kind of the same idea here, right? However, again, so instead of like building everything from scratch, x86 reuses parts of previous logic. And specifically, it will be using this map function, which we just discussed, right? So let's take a look how it's done. Okay, so sure. So alloc-UVM says, okay, sure. Are we running out of space? So obviously the user memory cannot be larger than 2 gigabytes. So if it is, then we just simply abort. After that, we say, look, we're mapping the entire region. So we take the old size and round it up to the next page, because we assume that there are certain assumptions here, which is slightly like odd in terms of x86, but we assume that the old address is already mapped. And we say the new address will start here, right? So we will start mapping those pages. And then we run in a loop here. So we say, look, for each, essentially what we're talking about is the region of memory. So it's some number of pages which we're mapping. We're running in a loop saying, okay, for each element, for each page in this region, use this kalloc function. And do we still remember? Let's just quickly do a poll. Where does the memory come for this kalloc function? Let me quickly enable it, which will make sure that everyone is awake. And let's do a free form response. Where does this memory comes from? Guys, the first 2 answers kind of scare me. One is system, another is heap. The third one, good one. Between the and symbol of the kernel and a fist stop. That's the right answer. It's a kernel memory allocator. Another answer is kernel address space. That's probably not a good one because it's not specific enough. Present. So where are we? Like people in the class answered? Still typing? Oh, I accidentally deactivated. Okay, yeah, submit. So again, the question is borderline trivial, right? So, but it's still important. So as some of your classmates mentioned, the way it works is we have a kernel memory allocator, right? So essentially, remember, we said, okay, sure, we'll track all available memory starting from the end symbol of the kernel, because we know that this memory is already taken by the kernel binary. And originally, we went from the end symbol to the end symbol plus 4 megabytes. Oh, not plus, like specifically from 2 gigabytes to 2 gigabytes plus 4 megabytes. But later, we didn't cover it in class yet. We extended this memory allocator to contain all memory up to fist stop. And essentially, it's a linked list of available physical pages, essentially. And every time you need a page, x86 allocates a page from this list. So let me close the poll for now. Do we understand how it works? Mm-hmm. That's a good question. So let's clarify. So imagine this is the physical memory of the machine. And imagine even it goes from 0 to 512 megabytes for the sake of example. The bootloader loaded the kernel at 1 megabyte, right? And at some point we said, look, this is the end symbol here. When we reach the main function and we switch to the entry page directory and later to the real page table, we mapped this physical memory with a 2 gigabyte shift, right? Like it's not up to scale, but roughly speaking, this is originally we mapped only 4 megabytes. So it starts from like 0 goes to 4 MBs and is mapped to 2 gigabytes to 2 gigabytes plus 4 MB, right? And so our original memory on the kernel memory allocator was the physical pages which were contained in this region up to 4 megabytes, right? So which were mapped somewhere here, right? I kept, and it's written in a book. So if you were reading the book and everything, but we'll come back to it in a second. Like the reason we did only the first 4 megabytes, because in order to maintain the list itself, since we're writing every time we adding an element to the list, we have to make a write, update the pointer, and it's a virtual address, so it has to be mapped. Otherwise, you immediately get a page fault, right? So originally we only did like 4 megabytes from the end to 4 megabytes, but then x86 initializes itself and goes up to something what they call fistop. And this is a symbol here. It's roughly 234 megabytes, right? So, and all of this memory from the end symbol to the fistop will, by the end of the main function, it adds all of this to the memory allocator. It's not like, there is a couple of subtle details here. So it's not all available memory on the machine because it says, okay, I make a simplifying assumption. I don't care about, I don't try to figure out how much physical memory machine has. I'll just go up to the fistop, right? So some physical memory may not be used. However, it just like says, okay, look, everything from fistop, everything from the like from 0 to fistop is mapped at 2 gigabytes to the 2 gigabytes plus this fistop. Make sense? I mean, let me show you. So yeah, so it's not super hard. I apologize. I didn't come back to this, right? So let me close this presentation. Like switch to the source code. So it happens if originally this kernel memory allocator init added up to the 4 megabytes here. Let me just maybe make it a little larger. It's the same main function, right? Before even exiting the main function, or we add all available memory up to fistop. And the reason we couldn't add all of it because some memory wasn't mapped. So we first mapped from end to 4 megabytes. Then we initialized the page table. So roughly speaking, one can argue that this function can be moved at line 22. But maybe I'm missing something, and maybe it will. Right. Correct, because the page table, like the way we construct the page table was this map function, right? Remember, we just talked about it. So the map function itself, let me show you here. The map function, every time we like essentially start doing this loop, which sets up the new page table for the kernel, essentially it returns it. Like we called it from main, kvmalloc, setup kvm, does this loop, and this loop essentially maps those 4 regions, 1, 2, 3, and this one goes up to fizstop. And after that, we're free to access pages which are here, which are above the fizstop. Like I don't show the fizstop, like I don't show above the end. So end is roughly here, right? Because it's somewhere past the kernel data section, right? And so everything then available, and then you can add those pages to the memory allocator as well. Make sense? Okay. Any other questions about the kernel memory allocator? So essentially, okay, we're mapping a region, going in a loop one by one. Each time we have a new page, we set the page with zeros because, okay, sure, maybe that page was previously used by the kernel, by other processes, especially by other processes, maybe they contain some secret information, sensitive information, like, you know, encryption keys, whatever, right? So we set the pages to zeros to make sure that they are fresh. And at this point, instead of like re-implementing the logic of mapping the page into the page table, we actually reuse this map pages function, which we just see it again. But instead of a large region, we just simply map a single page. But why not? Because it's a function which maps a page in a page table. This is the, you know, like the virtual address is A. The physical address is this virtual to physical macro, because we got this page from the memory allocator. And those are the flags. Notice that we have this user flag here, making sure that this page can be accessed from previous level 3. But again, it's just the same function, map pages. So when you enter map pages, you say, look, page table, virtual address, size of the region, 1 page in this example, physical address of the page, flags, and internally inside the map pages, what it does, it just walks the page table. Remember, it takes the virtual address, figures out specifically the page table entry, and allocates the inner parts of the page table. We talked about it. We kind of like know what this function is doing, and maps the page. And after that, you know, like the loop becomes very, very simple. So you executed this map pages and go to the next iteration of the loop. And that's your alloc UVM. So essentially you said, okay, sure, I allocated the memory, and now I can load the stuff, the ELF file from disk into this memory. Make sense? So it's very, very simple. Just because we just said, okay, we're going to reuse the map page function instead of like mapping the page into the page table by hand again. Okay, cool. So we did this, we initialized the memory. Now our goal is to like load the stuff from disk. Load the stuff from disk, again, not super hard. Specifically, it's this part of the exec system call. So what it does is says, okay, sure, we're gonna, again, take the page table, take the virtual address, take the inode, location on disk inside the file, and the size of this region, right? And essentially just load from the inode, load it into this freshly allocated pages here. The reason we go into those details, because there's a couple of interesting details here. It's a little unusual. Remember, we took 2 arguments, this page directory and the virtual address. And roughly speaking, you say, look, at a high level, it shouldn't be super duper hard. At the very end of it, like the core part of it is just read something from an inode into this virtual address. Does it make sense? However, the question is the following. Can you read into this virtual address? Like, or more specifically, can you just simply, if you have a virtual address, can you just simply take data from disk and write into this virtual address? Let's write is probably a better word. That's a little tricky. So you can probably guess the answer, no, but why no? Correct, because we're actually running on the old page table, right? So let me explain what's going on. Just again, step back to what is happening. So I will maybe use two colors, maybe blue and green. So blue will be the process we're currently running in, invoke the exact system call, right? And we dropped into the kernel and we're running on a page table we didn't switch the page table, right? So this is the old process, the blue one. It invoked the exec. What we're doing, we're creating a new page table. I'll use a green one. And we're constructing the new address space for the new process, right? And what we mean when we say load something, we use this green virtual address, which has to be here, right? And for this green virtual address, like if you just simply say, let me use some other color. If we just simply say something like read inode into this virtual address, of course, since we're sitting on this page table, we will overwrite memory here. Does it make sense? Because control register 3, CR3 of the CPU, is using this page table. All the translations will go and will lead us to this memory, right? The trick is how to figure out this green address. Do we have access to this green virtual address, and how is it known to us at this point? We do what? Okay, hold on. So roughly speaking, maybe like you're on the right track, but because if we have physical memory, right? This is the physical memory. This page is sitting somewhere in this physical memory, right? I use black for physical. It's not mapped. It's mapped by the green page table, right? So I should probably use green color to make sure to show the mapping. So like this green page table maps this page, right? The blue, I will give you a hint. The blue maps it as well, but where is in the blue address space this physical page is located? Which virtual address in the blue address space we can use to access this physical page, which is mapped by the green virtual address? Correct. So what you're saying is that in this blue address space, if we have a physical address, if we add this physical address plus 2 gigabytes, since we map all the addresses, right? So we mapped everything from the and symbol to the fist stop. We mapped all these pages in all address spaces. So we have an and symbol and move forward. Then obviously this page is actually mapped in the blue address space with the address, which is physical address of the page plus 2 gigabytes. In other ways, you can say P to V macro of P of physical address. Does it make sense?
So this computation.
It's a little bit more complex. First of all, we only have the virtual address of the green, but we don't even know the physical address yet. So how do we figure the physical address first? Anyone knows how to figure out the physical address PA of this page, of the green page? How do we do this? In which one? Yeah, but which page table? Blue or green? The green one, yes. So like, yeah, great. So that's what I wanted to hear. So look, the virtual address, it's a virtual address in the green process. Green process has this page mapped. So we take the virtual address and start walking this green page table, right? We use this function, walk page table, which we have, right? And at the end of this walk, we will get the physical address of this, physical address of this green page, right? At this point, we say, look, we have the physical address. We will plug it into this P2V of this physical address, and we will get this address. Essentially, it will be a virtual address like in a blue address space. Make sense? And it will be just physical plus 2 GBs. So the trick here is that this is like, you have to kind of translate addresses between address spaces. You say, look, I'm running on one address space, on the blue one. I'm trying to access a page in a different address space, in a green one. I have a virtual address there, but I don't have to, I don't know where it's mapped, right? So you walk the page table, you walk the green page table, get the physical address of this page, so this page. And after that, sure, like in x86, you're lucky, you already have it mapped with this physical address plus 2 GBs. You use this P2V, you get the virtual address, and this is where you ELF, like you're gonna read this, read I will use this blue virtual address here, and you load the file from disk into this address, right? So, a little confusing, like, yet still deserves explanation. So this is what exactly is happening here. So one more time, the code is doing exactly what we just explained. We say, look, we take the virtual address, which is this, like we started from address, we have an index I, the virtual address is addr plus I, we walk the page table directory, get the page table entry. This page table entry, you say, look, because there are some flags, we truncate it to physical address, right? So it's exactly this, the physical address of the page we're trying to access. And then we're using this P2V of this physical address, which is mapped in our address space with a 2 GB shift. And this is exactly where we're reading the data into. Make sense? Any questions about it? Like, I get it. So originally it was confusing virtual to physical. Now we have two address spaces, and we will have to convert between them. But in practice, again, it's not super hard. So like, again, you just remember this diagram. Just make sure that you say, look, I have this address. I will walk the page table, get the physical address. The physical address is mapped in my address space. I will use this P2V macro to make sure that I can access it. Okay, so beside the conversion, really nothing really super hard happening here. So just this function read I, reads the I node. Essentially, we go into the file, read it into the user part of the address space. And at this point, we say, look, we have the kernel text, we have the kernel data, like we read them from disk. So this contains the main. In our example, it was ls that contains the data section. This is a text section of main, text section of ls contains main. This is ls's data section, right? So again, we allocated those pages randomly from a memory allocator that could be anywhere in the address space. But just to emphasize that this page, despite the fact that it can be mapped in the user part of the address space, it will also be mapped somewhere here with a 2 GB shift. All the memory which x86 is using is mapped, physical memory is mapped with a 2 GB shift above the end symbol. Again, you don't have to always do it, but it simplifies your work. Otherwise, you have to, like, if you don't have this page mapped, for example, you have to temporarily map it into your address space and then maybe unmap it, right? So that, like, real kernels like Linux do that, but x86 doesn't. So, okay, so we have the process and a text section. What else is missing? We need to get a stack, right? Sure, that's easy. x86 says, okay, I will just allocate a stack page. In fact, what I will do, I will allocate 2 pages. like it will use the same function, alloc UVM. It's just that you don't need to map anything in there. Like you don't need to load anything from this because stack just is not initialized and it's initialized to 0, right? So what they do here, they say, look, we will round up the size of the address space to the next available page, allocate 2 additional pages. And why do we do 2? Because we want to have, if we are very specific about the layout of this address space, the stack page will be this one. x86 want to have this guard page here. The guard page essentially guards your code. If you like running, like if you recursively invoke functions, at some point you will fill in the stack page completely, right? So if I zoom in, like if I do this, right? So I zoomed on a stack page, right? So like at some point the stack page may be full. And at this point, if you just simply allow it to grow further down towards the address space, right? What it means is that you will say, look, guys, I will probably accidentally may start overwriting the data section and maybe even the code section, right? In x86, technically, and in any operating system, it's technically possible. And it also opens an opportunity for an attack, something what is called like a stack overflow, right? And one possible way to prevent a subset of these attacks is to inject a page, which is called a guard, and R is here. This page is not accessible. The moment you try to access this page, you will get an exception, and the operating system will terminate the process, saying, okay, it's a SAC fault, right? Makes sense? And so the way x86 is doing that is that they allocate 2 pages, and they clear the user accessible flag of the second page, right? Making sure that user cannot access it. And here is a killer question for you. It seems to be wasteful because we say that the guard page is will not ever be accessed. Why are we really allocating a page and leaving it there and just removing the user accessible bit on that page? Correct, but technically speaking, you can just leave an unmapped page in a page table. You can just say, look, this page is not present. It seems to save you a page, right? Why are we allocating 2 pages? One of them will be wasted, the one which is guard. So why? Exam-worthy question. And that leads us back to the beginning of this class, today's actually, which is a little unusual. This one. Remember those checks? We were discussing them last time. We said, okay, sure, guys, the user can make up a pointer. And the only checks we're doing here, that the pointer is within the process size. What happens is this pointer points to an unmapped page. If we wouldn't allocate a page and cleared the user accessible flag, that page wouldn't be allocated in the address space altogether. But it's not reflected in our checks at all. It's almost like we have a gap in the address space, right? What happens then? It would open an opportunity for a user to say, look, a pointer which I'm passing points into this page. The kernel validates, they say, okay, look, this checks pass, right? Because it's lower than size. But then later on, this pointer is accessed by the kernel. Since the page is completely unmapped, the kernel gets a page fault. It's confused about what's going on because x86 has only limited support for page faults. And essentially, it's a panic. So it's a way to attack the kernel. However, if we allocate this page and just simply remove the user accessible bit, the kernel happily will write into this page because user accessible bit doesn't affect the execution of the kernel. The kernel will not panic, will not have a page fault. The user will never be able to read this data from that page, but at least we block this attack. Does it make sense? It's a little awkward, so it's like a shortcut in a good kernel like Linux, because if you try to push a patch into the Linux kernel, Linus Torvalds will tell you again, I'm not going to tell you what he will tell you, but you can try. but he will not allow you to waste a page. So really, Linux is carefully accounting all the pages. It has a map of the address space. In case of a page fault, it will know the answer that it's what's going on. But really, that's how x86 simplifies the job. Okay, let me stop here, and I will come back to exact system call real quick next time to figure out how we push arguments on the stack.